All right, today we're pulling back the curtain on a really fascinating piece of architecture called the Toy SLM. We're going to get right into the nuts and bolts of how it works, starting from its very foundation, its geometry, and building all the way up to how it creates a single, coherent global state out of nothing but simple local rules. Let's dive in.
So, to get our heads in the right space, let's start with a big question. What if intelligence isn't just about more powerful computers and bigger algorithms? What if it's actually about the shape of the universe the system lives in? This idea, well, it's the key to understanding everything we're about to talk about.
Here's how we're going to break it down. First, we'll cover the geometric foundation, that weird curved space the system calls home. Then, we'll get into the core computational loop, the engine that makes it all run. After that, we'll see how the whole thing keeps itself stable over time. And finally, we'll put it all together to see how this integrated global state emerges.
Okay, first up, the geometric foundation. This is probably the biggest jump from what you might be used to with other systems, and it's absolutely crucial. We have to understand why this thing's universe is curved right from the get-go.
You see, most neural networks work in what we call Euclidean space. You can just think of it as a flat piece of graph paper. The Toy Ψ SLM, though, it lives in a curved, hyperbolic space. The big deal here is that in this kind of curved space, the farther you get from the center, the more room there is. It expands exponentially. This makes it a natural fit for organizing things with a hierarchy, like a family tree or an org chart, where things branch out more and more. The geometry isn't just a box the information sits in. It's an active constraint that starts shaping the data before a single calculation is even made.
And the second fundamental rule is this. Everything is local. There is no all-seeing eye, no central command center telling all the pieces what to do. Nope. Each little unit, each cell, can only see and talk to the neighbors that are right next to it. Every single interaction is local. This is the bedrock of how the system organizes itself from the bottom up.
Okay, so we've got our curved universe and our local rules. Now let's look at the engine that actually drives this thing. It's a three-step process that repeats over and over, and it's really the heart of the entire system.
So, the whole process boils down to these 3 steps. Yeah, the names sound a little intimidating, I get it. But what they do is solve a really fundamental problem. How do you do regular math, the kind that works on flat surfaces, inside a universe that's always curved? Let's walk through it.
So, the first move is log map aggregation. Here's the thing about standard neural networks. They're designed to do math in flat spaces. So the system does something incredibly clever. It takes a little local patch of its curved world, grabs all the info from the neighbors in that patch, and temporarily flattens it out onto a shared surface. It's kind of like taking our curved globe and making a perfectly flat local city map of, say, just downtown Manhattan.
The source material has a fantastic way of thinking about this. It says, before talking, everyone enters the same flat room. It's such a simple but powerful analogy. To have a sensible discussion, you bring all the local players into one shared, flat space, where they can actually process information together.
Now for step 2. Once everyone is in this temporary flat room, a totally standard multi-layer perceptron, an MLP, just does its thing. There's really no secret sauce here. It's doing what MLPs always do. It crunches the numbers from that local neighborhood and figures out an update for that local state. The key thing to remember, though, is that this is all happening locally, inside that tiny flattened-out patch.
And this leads to another really profound quote. Intelligence happens locally, geometry decides where it's allowed. The MLP isn't just making up the system structure as it goes. Not at all. It's working within the rules and the structure that the geometry has already laid out. The geometry sets up the chessboard, and the MLP just makes the next move for a single piece.
And that brings us to step 3, the X map. We've done our math, we have our update, but it's still sitting on that flat map. We need to put it back into the curved world. So the system projects that update back onto the curved surface along a geodesic, which is just the fancy term for the shortest, most natural path on a curve. This makes sure the update snaps back into place perfectly without breaking the overall geometric structure. It's like taking our flat city map and carefully folding it right back onto the globe where it belongs.
So that's the whole 3-step dance. But this isn't a one-and-done deal. It happens over and over. So let's move on and look at how this loop creates a dynamic system. And more importantly, how it keeps itself from flying off the rails.
This curve to flat to curve cycle is basically the system's heartbeats. It's ticking away for every single cell, all at the same time at every moment. This constant parallel rhythm is what lets the whole thing organize itself, adapt, and change, all without any manager telling it what to do.
So, with all this local activity going on everywhere, you gotta wonder, what stops the system from just dissolving into chaos? Well, that's where something called topological regulation comes in. You can think of it as a kind of system-wide quality control. It's always monitoring the big picture, the overall connectedness of the information, making sure the system doesn't shatter into a bunch of isolated islands. If it starts to sense a part is drifting away, it gently adjusts the local dynamics to strengthen those connections and pull everything back into one coherent whole. And all of this brings us to our final and, honestly, most mind-bending section, the integrated global state. How on earth do all of these tiny, local geometric rules add up to something that behaves like a coherent, unified system? Well, it's the magic of emergence. When you let that simple, local, geometry-respecting loop run over and over and over again, something amazing happens. A complex, highly organized global state starts to form all by itself. It becomes unified, meaning all the parts are connected. It becomes differentiated, meaning different regions can take on specialized roles. And it's coherent, meaning it acts like a single integrated thing.
Now, sometimes this emergent property is informally called system-level consciousness, and we need to be extremely clear about what this means. In this context, that phrase is purely functional. It describes an emergent property of the system, an integrated informational manifold. This is not a claim about subjective experience. It is not about feelings or what it's like to be the system. It's an operational description of a system that can maintain a unified, coherent picture of its internal state. That's it.
And just look at how this creates a fundamentally different kind of system. This table says it all. A classic LLM, it operates in a flat global space. The Toy Ψ SLM uses a curved local space. In an LLM, the MLP has to create the structure from scratch. Here, the geometry provides the structure. LLMs scale by throwing more parameters at the problem. This system scales by changing the curvature. And that even leads to different kinds of mistakes. LLMs hallucinate. This architecture might run into what you could call semantic collisions. They really are apples and oranges.
And that leads to maybe the most important takeaway of all, summed up perfectly right here. Intelligence is not born from the MLP. It emerges from the disciplined back and forth between geometry and local dynamics. The smarts aren't just in the little calculator. They're in the entire process, this elegant dance between the curved world and the flat calculations that respect its rules.
So we're left with this one big, fascinating question. If a coherent, unified state of information can emerge from something as basic as geometry and simple local rules, what does that tell us about the fundamental nature of intelligence itself? Is it something we have to meticulously build, or is it something that will just grow if we create the right kind of space for it?